long short-term memory, an introductory into the concept in recurrent neural networks by way of an example. And our example will be training a machine learning model to guess the next character of the names of emperors of the Byzantine Empire. Once it's learned to do this, we can give it our own prompts, and theoretically, our model will try to reconcile our names against the data set it's given. The LSTM architecture just so happens to be the right way to make something that understands names as sequences of letters, which generalizes well. So, for example, all of the names that are being generated at the bottom of the screen were generated by the model. And so this is my name fed through the LSTM, and it's trying to reconcile the name Luke King Hughes in various different ways against the data set of names of Byzantine emperors. It's just kind of cycling through them right now. So as an overview, we'll introduce the LSTM architecture, so we have an understanding of why it's working. Then we're going to talk about the data set, which is the names of Byzantine emperors. And then we'll frame the problem of how we're, what we're actually trying to solve and why and how it will work. I'll give a really, really quick code demo. I'm not going to go into the details, but I'll just kind of show you that it does run and we can interact with it. We'll do a bit of analysis, and then we'll talk about, actually the applications have switched to the beginning of the talk. So, so then we'll just talk about some other stuff. Cool. So LSTMs were created by two computer scientists, Sepp Hochreiter and Jürgen Schmidhuber. The long short-term memory came as a result of a development in recurrent neural networks. So I'm not sure if people are probably in this audience familiar with regular neural networks. We'll kind of talk about what a recurrent neural network is in a second. In 1991, Hochreiter, who is the man on the right, he did an MPhil, which explained why RNNs fail to generalize on problems that people kind of expected them to work on. In 1997, he and Schmidhuber produced a paper, that's the abstract just on the right there, and it's cited by 55,000 people, so it's pretty important in the history of machine learning. There's a lot of stuff that happens with LSTMs today in machine learning still. And to quote Christopher Olah, almost all exciting results based on RNNs are achieved with LSTMs. So this is just a pull from the Wikipedia page on LSTMs. This is kind of a brief history of timeline. You'll see on the left that the development is in the late 90s to early 2000s, and there's kind of like a winter between 2000 and 2009 where not much was happening. And then all of a sudden, you see 2009, and then from 13 to 19, some big developments are happening. So in 2006, LSTMs were reconciled against biological behavior, and that kind of spurned some interest. And then in 2014 through to 2019, we've had massive developments in how they're used. In 2017, a paper, which some of you may know, called Attention is All You Need, is written, which proposes a new architecture that doesn't use recurrent neural networks. And since then, that's kind of become the future of natural language programming. But LSTMs can be used for other things other than natural language programming. That's what we're going to be using for today. For example, speech recognition, machine translation, image captioning, DNA sequencing. Basically, sequences are what this thing is really good at modeling. So I'm going to start to give you an intuition of what a recurrent neural network is by way of an example. This is a complete oversimplification, but I hope you'll participate with me. Can I get people to raise their hands if they know what the Fibonacci sequence is? I'll get three people to participate. So you may, in the black mask. Can you explain, do you know what the Fibonacci sequence is? How would you explain it?
A sequence of adding the prior two.
Exactly. You add the previous two numbers. Okay, so can I just get you to leave your hands up? I'm going to pick on two more people. I'll I'll pick on you to make it. Oh no, you're not. I'm not going to pick on you. I'll pick on you, James. Okay. I'm going to give you like 2 seconds to answer this question, and the whole point is that you will fail, and that's fine. It's got nothing to do with James. He's a very smart person. Can you just tell me what the 10th element of the Fibonacci sequence is?
Oh man. 37.
It is not 37. Okay, I would like one more volunteer. Maybe I'll go out the. No, I'll go back to you to make it, because I'm going to give you the easy one now. Given that the 8th element of the Fibonacci sequence is 21 and the 9th is 34, can you tell me what the 10th one is?
I believe it would be 55.
Tamika is correct. Thank you for participating. The point of this exercise is to show you that it is really, really important sometimes when you're modeling something to know what came beforehand. A normal neural network, you would have to manually tell it what the previous answers to the Fibonacci sequence were for it to be able to infer that it should add the previous 2 terms. It'll do that, but you'll need to tell it what the previous 2 terms were. A recurrent neural network is kind of like a for loop inside of a neural network, and so it will basically pass messages to itself with every iteration. So as you can see, this is really powerful. James, who's a very smart person, was unable to just off the top of his head get the 10th one because the context of what came before it was really important. So if we unroll a RNN, if we think of it as a for loop and we unroll it, what is happening here is it's basically the same copy of a chunk of a neural network. So I'm going to be very vague with these terms here and not technical, and you can and you get a much better explanation of someone else than me. But if we think of A as a chunk of a neural network, we can think of an RNN as predicting on a sequence and then passing a message to the next iteration of the sequence. Okay? So it basically does this by taking the output from the sequence and then passing it into the next iteration of running the model. So as you can see here, A, when predicting on xt minus 1, is giving you ht minus 1, so that's the first output, and it's passing in a message to the next run of the model. Okay? So it only gets to pass one message though, and that kind of becomes a problem, because if we have a really long sequence that depends on things earlier in the sequence, it becomes harder and harder for the model to learn to pass these messages really far. So this is called the vanishing gradient problem, and it's actually basically the reason that long short-term memory was invented. So it's entirely possible for an RNN to learn the correct way to pass messages over long distances. It just so turns out that it basically never will. And Seth Hochreiter, the guy who I showed you at the beginning, basically did some of the early analysis that showed that this would never work. And for mathematicians in the audience, an oversimplified way you can think about it is repeatedly applying a diagonal matrix to itself over and over again. The eigenvalues of this matrix, if they're slightly bigger than 1, they explode, and if they're slightly less than 1, they go to 0. And because we're dealing with machine precision and all kinds of other things, it basically means that the gradients either explode or vanish and cause it to not learn to pass things over long periods of time. So, how does an LSTM solve this problem? It does this by, we basically create some crazy architecture, and this looks really complicated. I'll give you the cliff notes of what this is. So don't stress out. I looked at this and I was like, what the hell is that? But we basically we force it to have an architecture in which it passes information over long periods of time. So, sorry, just let me my notes. So the caveat is that so it can basically pass messages in 2 ways now. It passes a message down the bottom and a message up the top. The message up the top is completely protected by the architecture of the network, and you basically can only do either really simple addition or forget what is in the vector that's passed along the top. So what that means is messages are forced to travel long distances along this kind of like this highway that runs along the top of the network. So basically what happens is the message that comes in from the last unit First, it passes through this X. That's a forget gate. The network decides whether or not the information, based on what it's currently being fed in, should forget the information that's being passed along this highway. And then the second gate, the pink plus symbol, is an add gate, where it decides whether or not it wants to add information to this highway. And because it can't do anything really complicated like a neural network would normally do, a neural network will normally perform all kinds of crazy, layers of activation and linear transformation. This is really simple, and so it basically forces it to remember things for long periods of time. That's basically the principle that we're working with here. And that is the equation. If you need it, I don't think it's worth going into, but it's there if you want it. So now that we know why an LSTM is kind of good at remembering things for a long amount of time, let's talk about what our data set is. So this is where the talk kind of takes a bit of a hard left turn. The Byzantine Empire lasted from about 330 AD to 1453 AD. 1100 years is a really, really long time. And you may be asking yourself, like, how could a data set that lasts 1100 years be something we can do modeling with? So there are 94 emperors. I think there's like an average of, sorry. And the Byzantine Emperor is actually like a kind of artifact of history. It's not no one in the Byzantine Empire referred to themselves as Byzantines. It's just a kind of cultural and legal extension of the Roman Empire. So just to give you a taste of why this data set ends up being okay to do modeling with, you can see that these emperors, that's their reign on the screen, so that's when they were the ruler. And you can see that it's a very diverse period of time. And so you might think they probably have really different names. They're actually all called Constantine. So that's why we can do modeling. They had convention, and their names are pretty similar, even though the empire lasted 1100 years. Okay, so where do we get our data set from? We'll get it by scraping Wikipedia. So this is the Wikipedia page for the list of Byzantine emperors. It's really easy using Python Beautiful Soup to just scrape the table that's on there. I did kind of go down some weird rabbit hole when I was doing this. You can see that I was visiting the page pretty frequently. I got into a weird Wikipedia fight on trying to edit the page so it could be scraped. They got reverted. It turns out that there are people more passionate about the Byzantine Wikipedia page than I am, but of course there are. So how do we actually translate this Wikipedia page into a data set? Good question. So we're going to start with a Wikipedia entry. I'm going to scrape that and clean it, and cleaning it basically just means making it lowercase because I don't care about case that much. I'm going to get rid of weird, funny characters, so dashes become spaces, and then I'll have a bunch of basically I have a list of names. So we actually get 100 of them. I'm not sure why we get 100. There are only 94 Byzantine emperors, but it doesn't stuff up the model, so it's fine. Then what we're going to do is we're going to turn it into an array of data that we can actually do modeling with. So obviously a machine learning model needs numbers, and so we can think of our data set as a three-dimensional array where the first index is the word number, the second index is the character of the word, and the K, the other dimension, is which character of the alphabet am I using. So when we're doing this modeling, basically this up the top is what we kind of conceptually think of. The model will see a partially complete emperor's name. So in this case, I've got Constantine the First, the Great, is my Byzantine emperor. I feed the model Constan with the underscore just indicates that's what's coming up, and it should predict T. And so that is the numerical kind of interpretation that the machine learning model is going to be thinking about. It sees this kind of sequence of vectors, and it should predict the next vector. And so keeping in mind that the LSTM is constantly passing information about previous runs of the model to itself, so it will think of this as a sequence of letters. It knows that C was first, it knows that O was second, and the LSTM architecture means it can remember things over great lengths of time. Cool. Let's actually see it in action. So, sorry, cool. Okay, so hopefully this goes okay. So I'm literally going to I'm doing this in Colab. I'm just going to run the Colab notebook. So it's just connecting now, as you can see up the top right. It should take a second. If not, we can just move on. How are we doing with time? Are we doing okay?
Yeah, engrossed. So yeah, we're going okay.
Okay. So I think this is run. Does it run? Yeah, here we go. Okay, cool. I've got some text outputs. I'm not going to run you through the code. I can give you this Colab notebook if you're interested. I'll probably post it in the Slack afterwards. So and you can run this yourself. So here are some examples of the names we're seeing down the bottom. If you can see this here, a random sample of 5 names. So that's what we're feeding in. So now we have to build the ADS. So this is where we turn it into the matrices that we saw earlier. This is what the machine learning, this is what the LSTM actually cares about. Now what I'm going to do is I'm going to actually import TensorFlow and then build a model. So the way I will build this model is kind of just random parameters that worked. I can't really give you much more insight than that. I tried messing with the dimensions of the output space. 128 just seemed to work. I've got this other thing called recurrent dropout, which is interesting, which basically is telling it it's forcing it to forget more often. And what that will do is it will help us deal with our machine learning model not caring that we're diverging from the data set we have. So we might, so if we didn't have recurrent dropout, it would be really, really pissed off if I started writing the word const and then I changed my mind and started writing something else. The recurrent dropout is just going to make sure that it's comfortable with kind of moving between data sets. It kind of starts to forget about what the beginning of the word looked like a bit earlier. So cool. That is now done. And now what we can do is we can watch it train. So hopefully this will be fun. So I'm going to get it to spit out what it thinks are good Byzantine names at first. As you can see, in the first, without any training at all, it spits out absolute gibberish. So it spits out Dikivian Smorthlish and then 2 full stops. So it's really. Have you got a question, Torsten?
Now, can you zoom in a bit?
Oh yeah, sure. Is that hard to see?
Yeah. Thank you.
Is that better?
Much better.
Yeah.
Yeah, cool. So hopefully it runs a bit faster. If not, we can just go back to the presentation. But you will basically see this start to train. You know what? I'm just going to go back to the presentation. But we can come back to this at the end if we're still interested in that. Now I need to find where PowerPoint is. Okay.
Look,
Yes.
how did you get it to run? Because when you're at a certain other place, you have trouble getting it off of their hardware.
Yeah, I manually coded it again, and we can have a conversation about that later. That's an interesting problem in itself. But I'm not going to divulge my secrets in front of everyone. So, okay, so here it is training. I've taken a static shot of it training over here. Now you can see at the beginning, it literally has no idea what it's doing. It's spitting out random characters. You go down 1, and it's starting to look a bit more sensible. I'm not sure if you can see that, but I've seen this thing train like a million times, and I know when it's starting to look a bit more sensible. By the 3rd set of names, we are starting to see some structure. Isaac, not spelled correctly, but still, Paleos, Ikos, is that a Byzantine Emperor's name? I don't know, it could be. But then by the time I get to the end, we're getting exact copies. So Arcadius, Andronicus III, Paleologos, Isaac II Angelos. These are actual names. So it is with a random prompt, it is able to kind of spin this gold. So this is the loss over here, and it doesn't look pretty, but that's because we don't care that much about loss. And in fact, I've got a kind of fake validation set here. In the actual training of the model, I'm not going to have a validation set, which is a big no-no in data science. But I am going to feed it things that are not in the data set, and I want it to train on as much of the set as possible. So, okay, that's all well and good. We have something that can spit out Byzantine Emperor names, theoretically. How does it actually think? So what I've done is I've rigged up a GIF that will show us a heat map, which tells us the probability that the LSTM wants to predict the next letter. Now, I'll play it for you so you can digest what that means. It's actually predicting Ben's name. So I gave it the prompt Benjamin, and this is it completing it. So, so at the beginning, I'm forcing it to type Benjamin, so it really doesn't want to predict the letters that I'm putting up there, okay? But then as soon as it finishes writing Benjamin, it starts to do its own thing. And as you can see, it actually is making it's kind of making sense. So I don't know what Nosdund means. I think that is an error on the machine, on the model's part, not mine. But you know, it actually is predicting these things. So the closest Roman emperor to this is Justinian the second, the slit nose, and it's pretty close to that. You know, it's kind of close. It had to type Benjamin, so it's pretty close considering. So here are some interesting parts that I just thought I'd freeze frame on because it's kind of hard to digest as it's moving. Some of the cliff notes about like how this is working is you can see at the beginning when it's just got Ben, it really, really does not want to type J, but I'm forcing it to. So, just for your information, it doesn't know the word Benjamin, so it has no idea why I'm typing this. As soon as I get to Benjamin space I, it becomes interesting because now it has the freedom to predict whatever it wants. And here, it is guessing the next letter should be I. Now, the reason this is interesting is because the machine learning model really quickly learns what a Roman numeral looks like. It has the Roman numerals 1 to 11 in the names of emperors, and it really quickly learns that the second term is often a Roman numeral. And so it will do I, and then space. It'll often do IV. It really rarely gets X because it doesn't see it very often. But you know, it's pretty crazy that this thing learns Roman numerals, and it knows where to put them as well. So then as soon as you've finished the Roman numeral, Benjamin the second space, this is what the probability distribution looks like. So it really likes the idea of starting a quotation mark, which is what it does. It starts to try and write the slit nose. Some of the other options on the board are L, K, T, and C. And then you can see that at the end there, it really wanted to type E. But what I'm doing is I'm letting it do a random walk through this probabilities set. So basically, it's just a random shot weighted by what it wants to type. So it just got unlucky and the random number that was generated happened to spit out a D, but I really wanted to do an E. So it was almost there. So here's another example of one where it is almost 100% sure of what it wants to do the whole time. Irene, if I give it the prompt Irene, it types Irene of Athens 5 times. So it's really confident Irene of Athens. And that's because it's the only thing in the data set that looks like this. There's not too many other Irenes. If I give it some bad prompts, so if I just put in like 7 Fs or like 10 Ys, it has no idea what it's doing because it doesn't look like any other element of the data set, and it just flounders. So as you can see, under the stars is what it's auto-completing, and it doesn't make any sense. I put the top row of my keyboard in, Querdio, and it generated like something that was a bit closer to names, and that's because it saw a couple of vowels, but you know, it's not very close to anything. Those are the two things that I thought looked kind of similar to some of the things it generated. I put in Pedro, Stuart, and Ben's names as the organisers. So Pedro gets a bunch of things, but one of them looks pretty cool. Pedorios the second, Genikos, or the Logothete. There's also Pedronikos. I like Pedronikos. Pedronikos the third, Paleologo. So obviously it's trying to reconcile Pedro's name against Andronikos, and it gets pretty close. Stuart, it really likes Stuarakios, and that's because it looks like Staurakios, which is, I guess, your Byzantine namesake. And for Ben, I know we just saw Ben earlier, but there's some of the other ones. So Ben's is a bit more diverse because Ben's is a much more unusual name in the data set of Byzantine emperors. So then I also did myself and Kevin. So here are some of the examples. Kevin's is actually really funny, so don't watch mine. Kevin gets Kevinius, the. Can anyone guess what's going to come up? So Kevinius the drunkard. That's just one of the names in the data set. And cool. So I'll wrap it up now. What is the future? Or probably not even the future. What is currently happening? What I've got on the screen here are a bunch of the cutting edge NLP things that are currently out there. The word is transformers. Transformers are kind of revolutionizing NLP. And the reason is they can train on extremely large data sets, and then they can be applied to machine learning problems they've never seen before, and they do really well. It's what's called transfer learning, and it's probably the most important part of machine learning at the moment is getting machine learning models, or in the research area at least, getting machine learning models to learn and then apply that learning to new problems. An LSTM is a very, very bad transfer learner. So it will basically learn how to solve the problem you've given it, and then if you try to get that to learn or apply that to a new problem, it's basically like you're training a model from scratch. So if you're wondering where NLP is going, it's transformers, and I guess I'll leave it there. So thank you.
Thank you, Luke. That was great. Okay, any questions? And put your hand up if for the second question. I'll bring a mic to you.
I was just wondering, with the keyboards that you have with the heat maps, did you develop those yourselves, or is it some sort of package?
Yes, very good question. I've got this up as well, so we can start generating some names as well if you guys want to see it perform live. It turns out there's a very active part of the gaming community that wants to know how fast they're typing. So I tried to import a Python package called TapMats. It was completely busted, and then I just kind of like jerry-rigged it to do what I wanted. So that's what that is. But yeah, I did. So the answer is kind of.
Yeah, I really like that too. Any other questions, Luke? Other than what's my name? Byzantine.
Kevin?
Yeah, I think I just probably. So every time you showed us that, I'm going back to the model for LSTM, and basically every time you feed the previous output into the next iteration.
Yep.
Is that actually changing the weights actively?
So it's basically it's the same copy of the model. So it's the same copy of the model that's seeing the results of the previous iteration. So you effectively have like one model that is learning how to respond to old information. So it is actually the same weights and everything that will be trained. But it will have the context of, it's got the added context of what it spat out the last time. So yeah, good question. It's not just like a sequence of models, it is like the same weights, which is why it's so well suited to sequences.
All right, thank you so much.
Yeah.
Any other questions?
Does anyone, if you've got a question, I can just chuck your name in, and if you want to see what your name is, your Byzantine name is.
Anyone want a name?
Okay, Tamika actually. Tamika's will be interesting because I don't think it's a female name, and there aren't many like women's names in the data set. So let's see what it does. Okay, so it immediately wants to call you Michael because there are a bunch of Michaels in the dataset. So we got to Michael, Tamius, Tamiriani, Kirov, and Stantines. There you go.
Look to me.
Okay. Okay. So Kate's obviously not that interesting. Does anyone? Torsten. Actually, Torsten. I'm sure Torsten will have an interesting one. So what this is doing as well, I should say, it's truncating a random number of characters. I'm sorry, just jump back up. It's truncating a random number of characters at the end of the name, and then it's basically auto-completing it from there. So that's why you're seeing some of the letters change. So, Torsta Kuzenos, Torstio III, Torsak the Third Angelus. You got
Torsak's your new work name. What have you got?
we got one.
Just wondering, if you were to run it over and over and over again, you'd probably get like an average name, I guess, or most common name. Is that something which is like useful? Like one is, I would think, you know, is there like a theoretical average or most common way you can sort of work out based on these sort of modelling?
Well, so what I'm doing here is I'm doing a random walk on the probability weights, right? So for example, for Torsten, it's obviously for Torsak, which is all of our favourites. As soon as it sees the Tors, what it's doing is it's generating a probability distribution over the possible characters, and then it's generating a random number, and then it's assigning a letter based on that. What you could do is you could just use it as like a maximum likelihood, and you could just pick the letter it wants to choose most, in which case it would be deterministic, because the probability distribution won't change based on the sequence. So in that case, you would get whatever the model thinks is most likely. But the randomness is kind of a bit more interesting. Sometimes it doesn't fit to sequences really well. And also sometimes with the randomness, it'll choose a letter it didn't want to choose, and then it'll kind of like completely pivot its direction. If you just did the maximum likelihood or the like most likely, you'd get things that are really close to each other. So you can just get it to do that though. So you could, if you were interested in knowing like based on this sequence, what is the most likely thing? Oh, we've lost it. But yeah, does that answer your question?
Yeah, thanks. Yeah, I didn't think of that. And I guess the next step is to apply this to the sequence of the roulette wheel and see what's most likely. The next rate the wheel was biased.
Cool. Oh, sorry, you've got a question.
Jonathan, if you want to try it.
Yep, sure. Do you have another question, Jonathan?
Yeah. I presume the use with had Alexa up there that you can use this with words with a big enough corpus and a document term matrix. Does that need a lot of extra input to like control for actual English sentences?
Yeah, good question. So what I'm doing here is I'm letting it predict the next character, and so in that way I only need the characters of the alphabet, spaces, quotation marks, and a full stop to indicate that the sequence is over. If you were actually doing some sophisticated like language modeling, you would tokenize your corpus into words that are like, you know, that you expect to appear, and you'd have a much higher dimensional output space. So I'm basically giving it enough room to play with short sequences where all its tokens are the letters of the alphabet. Yeah, so definitely not in the realm of a sophisticated natural language model. James?
I think you might have just answered it, but how does it know when to stop?
Yeah, I did. Yeah, thanks, James. What I've done is I've taken in our data set, and I have basically turned it into a string and then put a full stop on the end. And tokenizing the end of the sequence is really important because the model does need some context for when it should end. as you could see in the beginning when we first started training this model, I think it has a maximum character of like, it can generate up to 60 characters before I tell it to stop. And in the beginning, it has no context for what even the end, like I don't even teach it what the final character is. It learns that itself. So, but without that context, it just generates random strings of characters.
So I have a question,
Okay.
which is,
Let me just.
why on earth? No, we've seen mine. We don't need to see it again. The purple ball. Well, it seems like Game of Thrones name as well would be that. Is why this subject, or just because like you picked it at random?
Yeah, that's actually a very good question. Thank you. The reason is a person that a lot of us here will know, Daniel Abdelnour. He is a much better machine learning expert in NLP than I am, and he got me to read a blog post by Andrei Karpathy. Andrei Karpathy is the head of AI at Tesla, and he is a savant. And he wrote a blog post called "The Unreasonable Effectiveness of RNNs," where he basically trained a series of RNNs to do things like generate Shakespeare and generate LaTeX. For those of us who know what LaTeX is, he generated LaTeX documents that actually compiled, generated Markdown. So like based on a Wikipedia entries of all kinds, like he basically took a chunk of Wikipedia and just got the LSTM to generate Markdown. Well, he was actually using an RNN, not an LSTM. But I read this blog and I was like, this is fascinating. And I couldn't believe, and it is unreasonably effective. So I have done very little to get this to spit out names that we all can laugh about because they are sensible.
Yeah, and I think using the Colab notebook's a good demonstration as well. So can you join me in thanking Luke for his presentation? Now, Luke, on your, I might go back